Hey there, welcome back to 2241. This is the examples 1 video for partial derivatives. All right, so here we're just going to start by computing a few partial derivatives. So we're given this function here. It's a polynomial, and we want to find the partial derivatives at both partial derivatives at the point 2, 1. So here's how we do this. So fx is like, or you compute it by doing this. Actually, I'm going to change my pen size here. Fx is 3x squared. So I compute the derivative of this term. And then I compute the derivative of this term as though y cubed was not a variable, as though it was an 8 or something. I just pretend it's constant. And so here I have 2x times y cubed, because my derivative is with respect to x, not y. All right, so then the next term is 0, because again, if y is constant with respect to x, then the derivative with respect to x is 0. Okay, so our first derivative in the x direction is 3x squared plus 2xy cubed. Okay, now we'll need our first derivative in the y direction, because we'll need to plug in the point later. So now I take my y derivative, and this term has no y's in it, so it's 0. The next term has x squared times y cubed. Okay, so that's going to be 3x squared y squared using my power rule. And then the last term here is 2y squared, and so we'll have derivative 4y. So here's our final partial derivative with respect to y. All right, now I need to plug in the point 2, 1. And if I plug in 2 for x here, I get 12 plus, and then y cubed, 1 cubed is 1 times 2 times 2, so 4 here. And then my first derivative is 16 at that point. So pretty steep line in the x direction at that point. All right, next up we have our y derivative. And again, we're just going to plug some stuff in, just like regular function evaluation. Okay, again, y is 1, so we can essentially drop it. And we get 3 times 2 squared is 12, minus 4 times 1 is 4. So here we get 8 as the value of the second, or the partial derivative with respect to the second variable. Okay, so nothing too special about that, just the concept of treating the other variable as constant. And in this one, we're going to do the same thing, just get a little more practice, but we're also going to interpret these guys. So we might do that by drawing a sketch. All right, let's see. Partial f, partial x. Okay, that first term is constant. That second term is not constant with respect to x. This last term is also not constant, but with respect to x, it is constant. It involves x in no way, so the derivative treats it like it's a 3 or something. So we've got 0 minus 2x minus 0, and that's just negative 2x. All right, our second derivative here, partial of f with respect to y. All right, same thing, we get a 0 here, now we get a 0 there, and last we get 4y. So this is minus 4y. All right, so now we want to find and interpret these two derivatives. So for that, we can just plug in 1, 1. And here we get minus 2. And here we get minus 4. And so if we draw a sketch real quick of what our function looks like. I want that to be yellow, since our coordinate planes are usually yellow. So this now is where we graph our function, and I'm going to make this, well, the function itself looks like an elliptic paraboloid. And elliptic paraboloids move upward or downward, just like a regular paraboloid. Okay, and so here we have our elliptic paraboloid, where the cross sections parallel to the xy plane, x and y, are ellipses, and the partial derivative that we're interested in happens at 1, 1, which let's say is right here. And so if we draw a tangent plane at this point, it should have slopes in the x direction of -2 and in the y direction of -4, so pretty steep there. And then the tangent plane is going to look something like that. We just draw it briefly. Okay. So there's our derivatives of the elliptic paraboloid. Let's look at this next function. This one has an unfamiliar form, so we're going to have to do a little bit of different stuff here. But again, we're just taking derivatives. So let's see, f(x), that thicker, f(x), there we go, of x comma y is, all right, I need to take the x derivative. All right, now here's the rub. This part inside is itself a function of x and y, and I'm applying the sine function to it. So what I need to do is apply the chain rule. Here's how this works. We're going to do it very carefully. I say u equals x over 1 plus y. All right, and now this thing that I'm computing is the derivative of f with respect to the single variable u, and then times the partial derivative of u with respect to x. Okay. So I'm treating f as though it's a single variable function of this other variable that depends on my two variables, x and y. It's just the chain rule, like we've dealt with before, but in the context of partial derivatives now. Okay. So df du, okay, derivative of the sine function is cosine of u, and now we multiply by the derivative of u with respect to x. And that we can compute over here is 1 over 1 plus y, again, because y is constant with respect to x, and so it is treated like a constant. So we have times 1 over 1 plus y here. All right. Fy then is the same idea, df du, but now times the partial of u with respect to y. All right, so we still have cosine of x over 1 plus y in front, but now we're going to multiply by the derivative of this function right here, or this one, with respect to y. And so we should go ahead and compute that separately as well. And that, again, now x is constant. And so we get, by another chain rule application, we have minus x over 1 plus y squared. Okay. And so that is what gets put over here. Minus x over 1 plus y squared. Okay, and we can simplify this if we want, but I don't care to right now. All we care about is getting through the derivatives. All right, next up, we have something kind of interesting. This is an implicit equation of x, y, and z. So I can't solve this for x, y, or z on their own. And you could do it using the cubic formula, but it would be a real pain and it would not be nice. So instead, we got to learn how to take implicit derivatives. Again, same idea, just treat each variable as though it's constant with respect to the one that you're differentiating. So let's see, dz dx. So now I'm pretending that z is a function of x and y, and I'm taking the partial derivative with respect to x. All right, so here I get 3x, so we're looking 3x squared, y is constant with respect to x, so it's 0, plus 3z squared, partial z, partial x, chain rule happening right there, plus now, all right, this is going to be interesting because it's a product rule. So we have, where's our product? This function times this function, and now our product rule says take the derivative of 6xy. So that's just going to be 6y times z, leave that alone, plus now 6xy times the derivative of z. All right, and on the right side, 1 is a constant, so its derivative is 0. All right, and now what do? We solve for dz dx. So let's see, if I collect all my terms, I have 3z squared plus 6xy dz dx, and that's equal to minus 3x squared minus 6yz. Okay, so then dividing everything over, I get dz dx equals minus 3x squared minus 6yz all over 3z squared plus 6xy. Okay, so there's our x derivative, and we're going to do the same thing to get the y derivative. So I'll take my derivative with respect to y, and now the first term will disappear. So we have 3y squared plus 3z squared dz dy plus, okay, now I'm taking y derivative, so I should have 6xz plus 6xy dz dy, all equal to 0. All right, same thing, we're going to collect our terms. 3z squared plus 6xy, partial z, partial y, equals minus 3y squared minus 6xz. And finally, we solve for the partial with respect to y, and that gives us a similar formula, minus 3y squared minus 6xz over 3z squared plus 6xy. You can go ahead and cancel the 3's if you want. Again, I don't care to simplify these too much. All right. And for our last one on this page, we have a function of 3 variables now. So we'll just see how this works when you have a little bit more going on. Nothing changes. We just treat the other variables as constant, except now we're treating one variable or 2 variables as constant when we differentiate with respect to the other. And then remember that we usually write 3 variable functions as, that's awful, w equals f of x, y, and z. I have to zoom out a little. There we go. All right, so now I want fx, fy, and fz. So let's see, dw dx. If I look at this function right here, it only has an x in the log part, so this whole e to the yz gets treated like a constant. And I take the derivative of log times the derivative of this with respect to x. So I'm going to have e to the yz power times 1 over x plus yz times the derivative of this with respect to x. So that's a 1 and that's a 0. So times 1. Right? And so our derivative with respect to x is this function. All right, let's do dw dy. All right, so now I've got y's in both factors, and so I need to do a product rule. The derivative of e to the yz with respect to y, z gets treated like a constant, so I do a chain rule and bring it down. E to the yz. And now I leave the log alone. Plus, now I leave e to the yz alone, take the derivative of the log. So we have e to the yz times 1 over x plus yz, and now the derivative of this using the chain rule. Okay, x is 0 with respect to y, and yz, derivative of y is 1, so the constant value z gets left over. Z. Right, and if we wanted to simplify this, we could write, let's see, I think z e to the yz times log x plus yz, and then plus 1 over x plus yz here. All right, so that's our y derivative. All right, last but not least, we'll take our z derivative. And notice that we actually have a little bit of symmetry in the function here between y and z. So I don't actually have to think too much here. What I mean by that is that if I were to swap the positions of y and z, replace y with z and z with y, the function looks the same. All that happens is that the variables go in different places. So this then, I can just read off from here as y e to the yz log x plus yz plus e to the yz 1 over x plus yz times y now. And so that gives me z e to the yz times the same sort of thing here. Not z, sorry, y in front there. Y plus 1 over x plus yz. Okay.